Who can tell me the path of this ball? Lewis, go get it! You're not a good retriever. Hello, everyone. Welcome back to a video from the Mathnasium. I was just throwing a ball because it's a good segue. And also, let me adjust that. There we go. Because it's a good segue, but also because I'm trying to entertain myself on this Tuesday evening and others. Let's get started talking about modeling data with quadratic functions. So this is kind of mistitled. I would kind of call this more a introduction to quadratics and some of their features and their parts. We're just getting used to doing some quadratic math. It's gonna be a good time. Now, I just chucked a little basketball here just a moment ago, and the path of the basketball, when I was talking to students in class, they said it was an arc. An arc, right? Arc is actually it is a segment of a circle, right? So if it was an arc, it would look like this. But when I throw a ball up, right? It kind of can be really long and narrow as well, so it's not an arc. It actually follows the path of a shape called a parabola. We're going to go over a parabola's parts today. You also need to know that almost anything that is affected by gravity is going to be able to be is in some way related to a quadratic function. And so the first bit of data that we're going to look at here, that we're going to kind of talk about, is having to do with the speed of vehicles, and when people slam the brakes, how fast the vehicles come to a stop. Now, I have to convince you that that there's a need for what we're doing. Like, I can't just toss a ball and expect relevance to be present. So I guess what I'm saying here is, why are we interested in these functions? Well, you should be interested in every function because when we collect data, we want to be able to summarize that data and fit a model to make a prediction so that we can say something about other potential stopping distances for a car, or whatever data we are modeling or trying to talk about. Okay, maybe we're looking at time on a diet versus weight loss, something along those lines. Maybe they can be modeled with a line. Maybe a line is the best model, but maybe a curve, or maybe an arc, maybe a curve or some other function models the data better. So let's take a look at this example. The table below gives the stopping distance for an automobile under certain road conditions. Let's say that is, assume that it's a dry road for this case. Below you have a few statistical models. The first is a graph. You have a line, and the second is a parabolic or quadratic model. Which do you think fits the data better? And you can't see those right now until I pull them up in Desmos. So let's take a look. Here's our data that's been graphed. I've got these 5 data points. These are the data points that are right here in this table. We can see them, and in Desmos you can actually fit different models, and it will do the math and talk about how good of a fit it is. Let's first take a look at the line. So I'm going to turn the line on, and you can say, like, whoa, those points are really close to that line. The line does a good job of predicting where the data is going to go, right? Yeah, that's pretty good, right? This one's a little high, this one's a little high, these ones are low. But if we were to fit a quadratic model, which is what we see here, it kind of says ax squared plus bx plus c. We're fitting a quadratic model. You'll find that the quadratic model actually passes through the points perfectly. Now, if we're trying to make accurate predictions about stopping distances for this car, whatever car it is at various speeds, then we want the model that's going to fit the best, because understanding this could be a matter of life and death. Yeah, so we want the most accurate model we can get. And it turns out the quadratic actually fits this data perfectly, which may not be perfectly apparent from the table. There's nothing in here necessarily that jumps out at me as saying, yeah, it's a perfect quadratic model, but it is. These are perfectly quadratically related. And where that comes in handy is, like, for example, if we were to predict something that there's no green dot for, the quadratic model would be accurate, and in this case, the line would be an overestimate. So that's where we're coming to. It's kind of a statistical reason why we're looking at different models, and one reason quadratics are important. So how do you tell whether something is linear based on its equation versus it's a quadratic? And it's really quite simple. Whenever you graph something of the form ax plus b, well, you've seen this before. That's just like saying y equals, let me change my color here, and we'll go red. That's just like saying y equals mx plus b. It's the same thing, right? Ax plus b, where a is not equal to 0. The graph is, it is a line, or it is linear, right? Okay, y equals mx plus b, your graph is a line, we'll say that it's linear. And basically, the highest power of x that is present is 1. Whenever you graph something of the form ax squared plus bx plus c, where a is not equal to 0, this is kind of a U-shaped. It doesn't really look like a U because it's kind of more slanted than a U, but we'll say it's U-shaped, I suppose. It is called a quadratic, aka we'll also say, it is a parabola is the name of the shape. Okay, so anytime you can tell something is quadratic is if you look at the equation and you see that the highest power of x is 2. If the highest power of x is 2, then it is a quadratic. If the highest power of x is 1, then it is a line, or it is linear. Okay, let's keep going. So let's take a look at a couple of examples of functions that are kind of mixed up and jumbled up, and we're going to decide whether or not they are linear or quadratic. Now, if you take a look here, this expression in a is not simplified. So we can't say it's linear or quadratic because we haven't carried out all the operations that are possible. So we're going to have to apply the distributive property to see what's going on here. And then we get x times x is x squared, and x times 3 is plus 3x. Okay, and if we take a look, now that this is simplified, I can't combine these like terms. This is as simple as it gets. We can see that the highest power of x is 2, so this is a quadratic. Okay, and then over here in example B, we are not distributing the minus x here, we're subtracting x squared. And so the only operation between here is subtraction, so all we have to do is drop the parentheses, and we'll get x squared plus 5x minus x squared. These two are like terms because they both have x squared, so we can add their coefficients. 1 plus negative 1 is 0x squared plus 5x, and 0 times x squared is just 0. So we just get 5x, and in this expression, the highest power of x is 1, so this is linear. Okay, and let's do our last example here. Identifying linear and quadratic from an equation or function. Okay, so here we have, we're multiplying two linear binomials. That's what these are called. And when you multiply, so this is a monomial. It's one thing times a binomial. So we say this times this times this. Well, here, what we're doing is we have to use a different multiplication technique. There's many ways to describe how to do this. I'm going to do it in as simplest the way I know that confuses kids the least, long road, and that is just make sure everything from the left group multiplies everything in the right group. So that is 2x times x gives us 2x squared. 2x times minus 4 gives me minus 8x. And then in the second group, so we've done 2x has multiplied each of these. Now 3x has to multiply each of these which will give us plus 3x and minus 12. So your teacher in the past may have called this foiling, first, outer, inner, last. I don't like foiling because I don't like using the term foiling because it doesn't work if one of them has 3 terms. The technique falls apart. So instead, I kind of think about like it's 2 cars go into a party. Everybody from this car introduces themselves to everybody from the other car. So one introduction, they have to introduce these people that are going to the party, and 3 has to introduce himself or herself to these people. And so it's all of these are multiplication. So now we can go through and combine like terms. These 2 x terms are the same, so you'll get 2x squared minus 5x minus 12, which is in simplest form. And the highest power of x is 2, so this is quadratic. All right, let's move her on. So when we have a parabola, there are 2 parts of the parabola that are of interest to us, okay? So parabolas can look 2 different ways. They can be kind of opening up like this, and they can be what we call this opening up. We'd say this opens up, and they can look like this where it opens down. Okay. This opens down. So the 2 pieces of quadratics are the 2 parts that are important to us. The first of which is this maximum or minimum value, which we call so it's this point that the point where it reaches the highest or lowest value. This is called the vertex. So the vertex is the point that is a maximum or a minimum for each of the parabola. So if it opens up, you will always have a minimum, and if it opens down, you will always have a maximum. Okay. Now it's important to note every parabola is symmetric, and there is a line around which it is symmetric. We call this the axis of symmetry. So the line about which a parabola is symmetric is called the axis of symmetry. And symmetry really means that one side is a mirror image of the other side. My drawing is not perfect, but that's incredible that I can throw something up into the air and it will create this perfectly symmetric parabola. So the axis of symmetry is the line that divides the parabola into 2 pieces that are mirror images of each other. Okay? This is the axis of symmetry here in red. Okay? I'll just say AOS. The axis of symmetry. Okay? Super. All right, let's go ahead and jump right in. We're going to do a couple examples and look at a couple graphs. I need you today to be able to look at a parabola, identify the axis of symmetry, and identify the vertex. And it's important to note that the vertex always lies on the axis of symmetry. Always. And it's very rarely that you get to say always in mathematics. You almost always never get to say always. Identify the vertex and the axis of symmetry of each parabola. Okay, so I'll go through in green. We're going to identify the vertex in green, or I'll do it for the first one. You can try it for the second one. So my vertex, this is how I'd like you to show your answer. My vertex, colon, is a point. It is the point 1, -1. And in blue, my axis of symmetry is the line that the vertex lies on. It's the vertical line. It's the line around which this is symmetric. The axis of symmetry, you can abbreviate it like that, is the line. It's a vertical line, so that line will begin with x equals. It is x, the line x equals 1. Okay? It is all the points with the x value of 1. That's why we say it's called x equals 1. Okay, now what you're going to notice here is that Since the vertex is always on the axis of symmetry, whatever the x coordinate of the vertex is always the number that goes in to the axis of symmetry. When you write them down, please don't just say 1, say x equals 1. Write the equation of the line of the axis of symmetry. Okay, you could try this next one, and then I'll go over here in just a second. Hold this up a little bit. There we go. That's better. I can finally sit up straight. Okay, here we go. Vertex. The vertex. Vertex in this case is -1, 2. And the axis of symmetry is the line x equals -1. It's always the same there. Okay, cool. All right, let's keep rolling. So I want to explain what this is asking first before we go over, before we start doing it algebraically. So what it's saying is, let's take a look here. Let me go back into Desmos. Let me delete. We're going to add a new table. Purple points. I'm going to put 1 point in there. It's the point 1, comma, -5. Our house is full of laughter today. Equals y equals x squared. And then I'm going to add a slider, -c. And what the slider allows us to do, and let's go back to home. What the slider allows us to do is it allows us to change the value of c in this equation. So what the problem is asking us is saying, it's like we have a parabola that is of this form, and I want to know the value of c that's going to contain this point. So in Desmos, we can sit here and we can slide this up and down, and we're sliding it down until it crosses that point 1, comma, -5, and then we can look up and find that, okay, it looks like it crosses right there. The value of c is 6. So the equation of the line that contains this point is the equation y equals x squared minus 6. So let's now do that with the following equation. So how do we do this algebraically, find c? Well, we know that any point that's on a line is going to make the equation true when we plug in x and y values. So really what we do is all we have to do is plug in our y value, -5 for y, and then we plug in our x value, 1 for x, and then we're going to solve the equation. So I'm going to simplify the left side, simplify the right side, 1 squared is 1, and then solve for c. There's a couple ways we can do that. I'm going to subtract 1. We'll get -6 equals -c, so c equals 6. So what we just did in Desmos matches up with the algebra that we're doing as well. So technically it just asks us for the value of c, but the equation of the parabola of this form that passes through that point is the parabola x squared minus 6, y equals x squared minus 6. I don't need to box that because that's not the answer that it asked me for, but just out of a habit, I just did it. All right, cool. Let's take a look at a couple more examples. All right, let's go ahead and do. Switch to my pen there. Why is it? It's stuck on my eraser. I hate it when it does this. Hold on, just a second. I'll be right back. All right, I got it. All right, so let's take a look here. Let's try this one. I'm gonna have you guys. Do the last one. There's one more, I think. Yeah, I'll have you guys do the last one on your own. We'll do this one together. All right, so I'm gonna plug in 25. Whoops. I'm gonna plug in 25 for y, and then I'll plug in 0 for x. Okay. So anytime I substitute, I try to use parentheses to show that I've substituted. 25, so we would say 25 equals 0 plus c is c. Anything plus or 0 plus anything is that thing squared. So we know that 25 equals c squared. So what number times itself is 25? In this case, there are two solutions. There are two numbers that when you multiply them by themselves, you get 25. One of them is c equals 5. One of them is c equals -5. So what does that mean graphically? Well, graphically that means, let's put our point on our graph. 0, 25. All right. All right. So x squared, or x plus c squared. All right, and we've got our slider for c. We're sliding this around, which is cool. We want it to travel through the point 0, 25. So let's take a look. That's this point right up here. It's kind of hard to see. Used to using CAD and dragging with my little mouse click. There we go. So here's this point 0, 25. How many different parabolas, how many different parabolas travel through that point? Well, when c equals 5, it travels through that point. When c is equal to -5, it also travels through that point. So that means there are two values of c, which means there are two different parabolas that will, or two different quadratics that will travel through that point, and we just showed you what they were on the equation. All right, you guys try this one on your own, give it a shot, and check your answer in just a sec. Okay, here we go. Plug it in. -1/2 equals -3/4 times 3 squared plus c. So we're solving this equation to get the value of c. I plugged in my y value of -1/2, plugged in my 3. Let's simplify. This is -1/2 is order of operations. Say that exponents have to happen first. 3 squared is 9. I'm going to write 9 as a fraction because I'm about to multiply it by another fraction. A little foresight there. Negative times a positive is a negative. 3 times 9 is 27/4. -1/2 over here. And there's a lot of people that were like, I don't want to deal with fractions. This one, there's a couple ways you can do it. I'll do it 3 ways, and you guys can pick the way that works the best for you. All of them are a fine way to solve this problem. Okay, the first way is using decimals. -1/2 equals 27/4 as I think -6.75 plus c. We can add 6.75 to both sides, and we'll get c equals 6.25. Perfectly acceptable way to solve this problem. If you did it with fractions, I think that is also perfectly acceptable. So you'll have this, and you'll just add 27/4 to both sides to figure out what c is. They need a common denominator. 1/2 in fourths is 2/4, plus 27/4 is 25/4. And 25/4 is 6 1/4. I guess we just need to do it 2 ways. That's probably fine. So you do it with fractions, you do it with decimals. There's even one other way where you get rid of fractions completely, but you'll have to come in for office hours to get that one. Something tells me no one's going to show up for that, but I'll be there. Hey, I'll be there. Just to take requests. You know, we could do some math together, office hours. Think about it. All right, team. That's it for video 1 from this unit. Thanks for watching. See you next time.